This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 4 of Week 5. Condensers and cooling towers. How a power plant rejects its waste heat, from steam to circulating water to the sky. We close the Rankine cycle in the condenser, size the cooling water flow, then take that heat to a cooling tower and solve for range, approach, makeup, and blowdown. The big picture first. A steam plant rejects its waste heat in 2 stages. The condenser closes the Rankine cycle. It condenses the turbine exhaust back to saturated liquid before the feed pump. A cooling tower then takes that heat from the circulating water and dumps it to the atmosphere by evaporating a small fraction of the water. The same heat passes through 3 balances: the steam side, the water side, and the air side. They all carry the same BTU per hour, so keep them straight and equate the heat only when you mean to. Start at the condenser. It condenses the turbine exhaust at constant pressure, back to saturated liquid for the feed pump, and the heat rejected is just the steam side enthalpy drop, mass flow times H in minus H out. H in is the turbine exhaust enthalpy, usually a low-quality wet vapor off the steam tables. H out is the saturated liquid at the condenser pressure, not subcooled unless told. One system insight: the condenser pressure is set by the cooling water temperature. Colder water means a deeper vacuum, more turbine work, and more net plant output. Now the water side. The circulating water flow comes straight from a sensible heat balance. The heat rejected divided by water's density times specific heat times the temperature rise. The heat rejected here is the same number from the steam side. This formula spits out cubic feet per hour, so multiply by 0.125 to convert to GPM. That's the gallons per cubic foot conversion, folded with the per hour to per minute step. Miss it and your flow is off by a factor of 8. The tube side pressure drop follows a modified Darcy form summed over the number of tube passes, with a combined entrance, exit, and reversal loss coefficient. Here is the full variable table: steam side, water side, and tower in one place. Steam mass flow, turbine exhaust enthalpy, and saturated liquid enthalpy come off the steam tables. The heat rejection rate and cooling water flow you solve. Water in and out temperatures are given. Then latent heat, evaporative makeup, and cycles of concentration carry you into the cooling tower half. The only constants you bring are the water properties, density, specific heat, and latent heat. Everything else is given or solved. Move to the cooling tower. 2 temperature differences define it. Range is the hot water temperature in minus the cold water temperature out, how much the tower cools the water. Approach is the cold water temperature out minus the ambient wet bulb, how close the tower gets to its limit. Here is the key trap. The leaving cold water sits at wet bulb plus approach, and a tower can never cool below the ambient wet bulb temperature, no matter how large. So the approach is always positive. Note it is the wet bulb that sets the floor, not the dry bulb, because the cooling is evaporative. And for sizing, a cooling tower ton is 15,000 BTU per hour. The water the tower loses has to be replaced. That is makeup, and it covers 3 losses. Evaporation is the largest. It carries the rejected heat away as latent heat, so it is the heat rejection rate divided by the latent heat of the water. Blowdown bleeds off concentrated solids and is the evaporation rate divided by cycles of concentration minus 1. Drift is windage, droplets blown out with the air, about 0.1%, usually negligible. Total makeup is evaporation plus blowdown plus drift. Evaporation dominates, but the moment a problem gives you cycles of concentration, you must add the blowdown term. Worked problem A. A surface condenser takes turbine exhaust at 100,000 pounds per hour. From the steam tables, the exhaust enthalpy is 1,020 BTU per pound. The saturated liquid exit is 70, and the cooling water runs from 75 to 95 degrees. Find the heat rejected and the cooling water flow in GPM. The plan: steam side for the heat, then the water side balance for the flow in cubic feet per hour. Run the numbers. Step 1. Steam side, 100,000 times the enthalpy drop of 950 gives 95 million BTU per hour, 95 MBTU per hour. Step 2. Water side. Divide that by water's density times specific heat times the 20-degree rise, and you get about 76,000 cubic feet per hour. Step 3. Multiply by 0.125, and you land near 9,500 GPM, a realistic big plant circulating water rate. Notice the 20-degree rise across the condenser is the tower's range. Worked problem B. The tower rejects that same 95 MBTU per hour. Take the latent heat of the warm water at about 1,040 BTU per pound and run 4 cycles of concentration. Evaporation is the load over the latent heat, about 91,000 pounds per hour, roughly 183 GPM. Blowdown is that over cycles minus 1, so over 3, about 30,000 pounds per hour, 61 GPM. Drift is negligible. Total makeup is the sum, about 122,000 pounds per hour, near 243 GPM. A gut check. The load over 15,000 is about 6,300 cooling tower tons. And the cold water leaves at wet bulb plus approach. With a 68-degree wet bulb and 75-degree water, the approach is 7 degrees. 5 traps. 1. A tower can never cool below the ambient wet bulb. Cold water is wet bulb plus approach, and the approach is always positive. 2. Forgetting blowdown. If you're given cycles of concentration, total makeup is evaporation plus blowdown plus drift. 3. Cubic feet per hour versus GPM. Multiply the condenser flow by 0.125, or be off by 8. 4. The condenser exit enthalpy is saturated liquid at the condenser pressure, not vapor and not subcooled unless stated. 5. Keep the 3 balances separate. Steam side, water side, and tower evaporation all carry the same heat, but each uses its own properties. Bookmark the 2 pages. The condenser heat rejected, mass flow times the enthalpy drop, with the exit as saturated liquid at the condenser pressure. The cooling water flow, load over density times specific heat times the temperature rise, in cubic feet per hour times 0.125 for GPM, plus the tube pressure drop. Range and approach, hot minus cold and cold minus wet bulb, with the ton at 15,000 BTU per hour. And makeup, the load over latent heat plus blowdown over cycles minus 1. 2 chapters, 1 heat rejection story. You now own the heat rejection chain. The condenser closes the Rankine cycle. The cooling water is sized from the water side balance, and the tower handles range, approach, makeup, and blowdown, never cooling below the ambient wet bulb. Next topic, we flip from rejecting heat to moving it, the vapor compression refrigeration cycle, where the same condenser becomes the high side heat rejector, and we chase coefficient of performance. Bring today's habit of always knowing which side of the balance you are on.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.